Okay, in this video we're going to derive the spectral density for white noise, and we'll see that this derivation is going to be a very easy one, but the takeaways are really important because white noise is such an important topic, important concept throughout time series and throughout the rest of our book, so it's going to be good to derive this. Now, where we'll start is the formula for the spectral density. So the general formula is given by S sub x of f equals 1 plus 2 times this sum of k equals 1 to infinity of the autocorrelations rho sub k times cosine of 2 pi fk, where f is ranging from negative 0.5 to positive 0.5. Now, that's a big formula. It's complex. And when trying to calculate that in practice, we're going to definitely use our R software to help us do that. We'll get into that later on. But for this particular video, we're concerned with the spectral density for white noise only. And that's going to simplify the calculation considerably because of the fact of how white noise is defined. Remember that for white noise, rho sub 0 is 1, which is true for all cases, because remember the autocorrelation for lag k equals 0 is always 1. But for white noise, it turns out that for any other lag, that is when k is not equal to 0, the autocorrelation is equal to 0. So the good news is that rho sub k of 0 gets put into this formula, into this sum, so our rho of k is 0 through all of these terms in the sum, and that means we're adding up a bunch of zeros. So that means that we can say then that the spectral density for white noise is 1 plus 2 times the summation of k equals 1 to infinity of a bunch of zeros, which is 1 plus 2 times 0, which is 1. So this says then that the spectral density for white noise is always equal to the constant 1. Let's plot this. We can learn some things from the plot. And our horizontal axis will be f. Vertical axis will be the spectral density, S sub x of f. And we've said here that our f ranges from negative 0.5 to positive 0.5. So we will make this 0.25, 0.5, and do the same thing going over to the negative side. And then for our vertical axis, we'll let that be 0.5, 1, and 1.5. But remember that we know that our spectral density is always equal to 1 for white noise. So that means that it will be a horizontal line at 1. And our spectral density looks like a rectangle. Since it's a rectangle, we can easily calculate the area. We know area is base times height, so the area of the rectangle is equal to 1. And that is consistent with the fact that we know that the area of all density curves is equal to 1. So that looks good. Another thing that we should remember is that spectral densities are symmetric. We've seen the property that S sub x of f equals S sub x of negative f. And we can certainly tell by this picture that we have this symmetry because the plot on the left side of the vertical axis looks just like the plot on the right side of the vertical axis. And for this reason, what we do going forward on our spectral density plots is we only plot the positive side, the positive f's. That is from 0 to 0.5. This left side we don't show. So that's important to realize going forward. And here's the takeaway. frequencies are equally present in white noise. And that's indicated by the constant spectrum. And another way to look at this is that among this frequency band, there's not one frequency that has an advantage over the other. And these properties are going to be important for us later as we go on, because a lot of times we'll want to determine whether or not a certain series is white noise. And one way to confirm that is to look at the spectral density and see if we see that it is very nearly 1 at all times. And if it is, that's an indication that the series actually is white noise. In this video, we'll talk about how we estimate the spectral density from real data. Now, in practice, we won't be doing this by hand, and we won't be doing it by calculator even. We'll let R do it, which uses the TSWGE routines to make this calculation. But in this video, we want to go into the details of the calculation because we can learn a lot from that and understand the process better by doing so. Okay, so where we should start here, of course, is the formula for the spectral density, and that's given up at the top here by S sub x of f equals 1 plus 2 times the sum, k equals 1 to infinity of rho k times the cosine of 2 pi fk. In the previous video, we looked at this very formula in the case of white noise, but for white noise, since the rho k's equal 0, it became very simple very quickly, and the answer was just 1. But this is in general, so we don't have that in this case. So what we do have to deal with is still these rho k's, and that's going to be an issue because we don't know rho sub k, because those are the population autocorrelations, which we're not going to know if we're just given a sample set of data. So that's going to be one thing that we got to talk about. Another issue is this infinite number of terms that we're supposed to sum up. We don't know how to do that. So these are the two things that we're going to have to look at going forward. So our two issues are the infinity and the rho k. Now let's deal with the rho k first, because the solution of that is pretty straightforward. It's what we do in statistics when we're trying to estimate a parameter. What do? We like to use the corresponding sample statistic, and that's exactly what we do in this case. So to estimate rho k, what we're going to do is use rho hat k to make that estimate. Now notice that implies that our new formula can be written as follows: 1 plus 2 times the sum of k equals 1, 2, I've left that blank on purpose, we'll be back to that in a minute, times rho hat k. So we've replaced the rho k with rho hat k times cosine of 2 pi fk. Now the next thing we should do is look in more detail of these rho hat k values. For example, let's let k equal 1 and think about that calculation. How do we calculate rho hat 1? Well, what that is that's the sample autocorrelation at lag k equals 1. You can tell by the formula what's going on here is it is averaging, there's the 1 over n, it's averaging the sum of these cross products divided by the variance sx squared, which is also the auto covariance at lag 0. We saw that in previously in some of the properties. So that's really what is going on formula-wise. Now, let's talk more about this idea about these cross products. How many of those are there? Well, the answer to that depends on what the lag is. For example, for lag k equals 1, let's suppose that you add n equals 1,000 values. How many cross product terms would there be for lag k equals 1 in a data set with 1,000 values? Well, there would be 999. And that's why this sum goes to n minus 1. Let's go to rho hat 2. Same concept for the formula. The only difference you'll see is that this goes to n minus 2, and this is t plus 2. Now, why does this say n minus 2? Well, again, in a data set of n equals 1,000 values, how many different cross product terms are there that would correspond to data values that are exactly 2 time periods apart? There would be 998 of those, and that's why this is n minus 2, and so on. It would seem like you could take that all the way out to rho hat n until we think about it. If we ask ourselves, how many cross products terms would there be, or how many data values are there in a set of 1,000 that are exactly 1,000 data values apart? The answer is none. There are none that are 1,000 data values apart. So therefore, this term cannot even be calculated. Well, what's the highest we can take this then? The highest we can take it is to rho hat n minus 1. For example, let's again use our n equals 1,000 example. If you've got 1,000 data points, how many different data values are in that data set that are exactly 999 values apart? Well, there are 2. x1 and x1000 are exactly 999 points apart. So there's only one pair of cross product terms in that. So therefore, when we're trying to write rho hat of n minus 1, we don't even need to write a sum term because there's only going to be one term. And it would be 1 over n times x1 minus x bar times xn minus x bar divided by gamma hat naught. So that is an interesting little feature of these sample autocorrelations. And that's going to be the reason that when we look at this sum, we're going to go to n minus 1. Now, another thing to point out about these sample autocorrelations, we just showed that the number of terms in each of these calculations is going to depend on the lag k. So notice that when the lag k equals 1, and suppose there are 1,000 data values, so you've got 999 different cross product terms going into that estimate, that's going to be a pretty good estimate for row 1. Same thing for rho hat 2. That's going to have 998 values that go into that estimate of row. That's going to be a pretty good estimate. But the further we go down this list, that is, the closer k gets to n minus 1, the worse that estimate is going to be, simply because there aren't enough terms going into the estimate to make it all that reliable. And that's going to come into play on the next screen. Okay, let's continue with where we were. Recall that we had established a newly revised spectral density formula and said that S sub x of f is now equal to this formula we see at the top, 1 plus 2 times this summation from k equals 1 to n minus 1 instead of infinity, and rho hat k instead of rho k times cosine of 2 pi fk. Recall that we had said that there were 2 issues with our original formula. One was the infinity, and one was the rho k. So it appears that we've got this resolved, but the issue is that this so-called sample spectral density is not a very good estimator. And the reason it's not a good estimator is because of the fact we established earlier that when lag k gets near n minus 1, it's not going to be a very good estimate, simply because there aren't enough data values going into that estimate to be reliable. So we have to do something to compensate for that. It turns out that in the 1960s, many time series analysts were working on this very problem, and they came up with something they called a smoothed window estimate, and that was what they used to address this. Now, the idea behind the smoothed window estimate is pretty straightforward. So let's talk about that really quickly. It really revolves around this fact. Since estimates for lags of k near n minus 1 are very unreliable, then it makes sense to either eliminate those or at least to minimize their effect, their impact. And that's exactly what this technique does. So here's what we'll do at first. How about we write the formula of S hat XF as just like it used to look, just like it did here, except let's don't go all the way to n minus 1. Let's stop it at m. So we're stopping this sum at m for some m less than n minus 1. Now, that seems a little vague itself. Where is that? Well, a rule of thumb would be m equals 2 times the square root of n. But I'm going to put a question mark here because that's not necessarily the final answer. It's not set in stone. What we may end up having to do is to increase that or decrease that value. And we see that in several of the examples in our textbook. How do you know to increase or decrease? Well, you want that spectral density to be visible, to clearly reveal the frequency content that you want it to reveal. And if n is too, if the m is too big or small, you won't be able to detect that. Okay, the final topic would be the window function and the choice of the window function. The window function is going to depend on a parameter lambda k. And it's going to also affect our formula. So it'll revise our formula for one last time. Put a star by this. This is our last formula. And it looks like this. S hat x of f equals lambda naught times 1 plus 2 times the sum of k equals 1 to m of lambda k times rho hat k times cosine 2 pi fk. And this is called the smooth spectral density estimator. Now, back to this concept of the lambda k's. What good does that do us? Well, it turns out that the absolute value of lambda k is a term that decreases as k increases. And notice that that's exactly what we want, because the problem with k as it increases is that it's not as reliable. The estimate is not as good. So it's convenient that this term in front of it, the lambda k, minimizes the effect of the rho hat k as k gets bigger and bigger. So that's why this works. Now, I mentioned the word choice a minute ago for these window functions. Well, as I said, in the 1960s, many statisticians came up with their own window function. The first one I'll mention is by Parson, and that's the one that our TSWGE code uses. So we're going to be looking at the Parson window. Our textbook gives the exact formula for the lambda k. I'm not going to include it here. But Parson, also Tukey had a window, a name you probably recognize. Bartlett also had a window with a different formula. So these are just 3 examples of window functions. And then the final thing I want to say is that, so we've got this smooth spectral density estimator that we now have. And what is the what's the purpose of these? Well, obviously, to smooth the spectral density. And secondly, what does that do for us? Well, we're going to be looking a lot at these spectral densities. And why? Well, the purpose for that is because we can tell a lot about frequency content of the data based on looking at these spectral densities. So that's the whole purpose of this, is to provide information about the frequency content of a data set.